Perseverance, the courage to ignore the obvious wisdom of turning back. Our demotivational poster for the day. We're going to study fasteners, frames, and welds in this section, and I put this first in the course even though it's near the end of the text because fasteners, frames, and welds are things that are ubiquitous. They're in pretty much every single machine. Maybe not welds in every machine, but certainly fasteners and frames are. There are many different fastener types. You probably have dealt with fasteners quite a few times, and hopefully you realize they range from tiny to huge. I mean, I have taken really small number 0 screws or so out of small cell phones when I've repaired them and replaced screens and things, all the way up to using, well, a bolt that really is not all that large. The largest bolt I've used in my private life is a 1-inch diameter fastener. It was a grade 8 bolt. There's a tremendous variety. There are bolts much bigger than that. There are screws and bolts smaller than that. And technically, usually when they get pretty small, they're a screw. So what is the difference between a screw and a bolt? Well, it's a technical definition. It actually has very little to do with the thread shape. You might think that a screw is just the things I've showed there at the bottom. They're sheet metal screws. But there are machine threads that would appropriately be called machine screws. A screw is a device that holds pieces together, and the female threads are in one of the pieces being clamped together. So you can see here in the middle, all of those are applications of screws, whereas a bolt is an item that has a nut on the backside. So you could actually use a sheet metal screw and make it a bolt by simply putting a nut on the backside of it and letting that be what actually clamps material together. That's the mechanical engineering technology definition of a bolt versus a screw. But of course, in all these fastener types, there's a tremendous variety of head types, drive types, lengths, obviously, whether they're full threaded or partially threaded. I want to show you an example of an application I had. I bought a house that had a sunken-in middle room, and I didn't like it. It turned out I ended up walking around it most of the time and hardly used the room. I decided to make that room just level with the rest of the house. So I ended up digging out the area and removing the dirt that was under that section of the house. And I ran some metal trusses, expanded, or what's called open web trusses, across the floor in the long direction. So I used steel for that reason rather than wood. They were a little more expensive, but they really weren't that bad. And I wanted to put down wood subflooring, basically some plywood. Well, somehow I had to attach the plywood to these steel trusses. So I thought, okay, do I really want to go through, and I calculated it up. I think it was about 2,000 holes I would have to drill and tap in order to screw into this. Well, that would have been a big pain, so I started looking around for specialty fasteners, and I found one much like this image that I've got on the screen on the right. And it was really interesting. It was a custom fastener for the sake of attaching plywood to steel frames like what I've got. And the steel on these frames is not just sheet metal. The steel on these I said frames, I meant joists. The steel on these joists had to be almost almost an eighth of an inch thick. So I think I measured it was about 100 thousandths or so, 0.1 inch or so. And so I needed something that could drill through, make the threads, and put the screw in and hold everything in place with just one operation. I didn't want to go through and make a whole bunch of holes and then come back and fill those holes with screws. So the fastener's a lot like this, and what it had was a drill on the end. It then had reamers, and the purpose of the reamer was to actually make a clearance hole in the plywood. And a clearance hole, if you don't know what that is, the clearance hole is just a hole that's a little too large so that the fastener's threads don't engage with that portion of the material. So obviously you want to pull the plywood down to the top of the joist. You don't want the threads to hold them apart. Anyway, so it had reamer wings, and what would happen when you drilled through the steel and then also reamed through the plywood, those wings would get knocked off by the steel. There's no way they were going to make the steel hole any bigger. But then where you see this marked as shank slot, there was sort of a cutout that looked a lot like this, and the purpose of that was to act as sort of a rudimentary tap. And so it would actually make the threads in the steel, and then of course the threads of the main fastener could engage with it, and then the head of course holds the top of or essentially grabs the top of the plywood and pulls it down so that it connects with the steel truss appropriately. And these worked wonderfully. I did end up buying a slow-speed drill from Harbor Freight, believe it or not, and it worked great. There was a Torx drive, like a starhead drive, and what that did is it allowed the fastener to be driven in with a lot of torque, more like a spline drive, rather than a Phillips or something. You may not know this, but Phillips are actually designed to so-called cam out. They're supposed to round off or keep you from driving them in too far where you bust the fastener. Now, that doesn't always work, especially if you push really hard on it. You can keep the bit engaged and end up breaking the fastener. But these fasteners were different not only because of the drive, but also the material they had made them out of. They made them out of good, strong material and heat treated them appropriately, so that the screws were much harder and much stronger and yet ductile still, where they can make the hole in the joists and hold the plywood in place. So if you have an application and you need a custom fastener, it's probably available. Set screws are another type of fastener. Of course, there's many other fasteners besides just these. We'll talk about a few other types. But set screws are typically used to hold collars onto shafts. Now, there are other applications of set screws, but by and large, this is what they're used for. Now, the common problem with set screws is that they so-called booger up the shaft. What that means is when you drive the set screw in, it's fairly hard, and it will deflect some material off the surface of the shaft, and that material will rise a little bit, and when you back the set screw out and try to pull the collar off, because the material has flowed up inside the area from the shaft into the area where the set screw is located, well, that locks the collar in place. It can be very difficult to get the collar off then. The simple solution for this, well, there's actually two. The first solution is to use what's called a dog point set screw, and so these types of set screws have a brass insert in them so that it's a very soft material, and as you drive the set screw harder and harder onto the shaft, it doesn't deflect the shaft material. It doesn't make cuts in the shaft. Rather, the set point, or the dog point, I'm sorry, on the end of the set screw deflects and deforms, so that when you back it out, the shaft's good to go and the collar can slide off. A more common solution is to include flats on the shaft. Now, it's actually preferred to put flats in the meat of the shaft, not out on the end, but most motors have the flat on the end, and the idea here is that the set screw should be mounted in the collar so that it goes down and engages with the bottom of the flat. That way, if the flat has little bits of material that come up from the set screw damaging it, it won't matter. The collar can still slide off. There are many locking methods. Some work and some actually don't work. You may have seen the first, which is called a jam nut. Turns out that even your book has this wrong. That's the wrong way to apply a jam nut. Jam nuts are usually thinner than the main nut, and you actually need to apply it the other way. It doesn't work to apply it this way. I've got a link here. If you download the presentation, you can follow it and see why it is that it's wrong to put the jam nut on top. But it has to do with the way that the jam nut moves and engages, whether it's the top flank or lower flank of the thread that engages. So follow that and know that your book got it wrong. Another way is to use these lock washers, but that link and others will show you that lock washers actually don't work very well at all when it comes to vibrations. As a matter of fact, these lock washers can cause the nut to back off quicker than if there was nothing there. Now, of course, the idea behind this is that this is supposed to be kind of like a spring, so that if it does loosen up a little bit, you still have some tension. But honestly, in most applications, these fail miserably, so I don't really recommend that you use them. Another method is a deformed washer. Now, the way this works is typically the washer is not completely deformed at first. You have to put it in place, put the nut in place, tighten it to the required torque specification or clamping force, and then deform the washer some so that the washer can't turn and the nut can't turn. Now, the next example, D, I've never really seen a nut held in place where you just drill a hole in the fastener above the nut and insert a cotter pin. What I have seen, though, is what's called a washer nut retainer. And it's actually very similar to the next item, which is E, which is called a castle nut. But this washer nut retainer actually has an advantage over the castle nut. If you put this washer nut retainer on top of the nut after it's been tightened, you actually have 12 points on this thing. So you can, whereas the nut is 6-sided, the washer is 12, and kind of like a 12-point socket, you can turn a half of a flat, half of a side. And that gives you more resolution so that you can line up the washer and insert the cotter pin without having to rotate the nut as much. Now, one problem with both this washer nut retainer and the castle nut is you do have to line it up. If the hole is made in the fastener before you apply the nut and tighten it down, you don't really have, I mean, you only have certain positions you can put the nut in, and that may not be the correct torque. Of course, if you've ever worked on the front end of a car, or you have a car that has rear-wheel drive, you've probably had to deal with castle nuts around the front end of the car. And castle nuts, of course, are a positive locking method where the nut itself has features in it that engage with the cotter pin, and it prevents rotation. No practical amount of vibration is going to make that come out. You destroy the components with vibration before that would back out. The next item on the lower row, F, is a schematic representation, just like the threads are pretty much schematic representations on most of these figures. What it really means is that you deform the nut. Now, I rebuilt the engine in my car. I drive a diesel Jetta, and when I rebuilt it, I had to take the cylinder head off. That means I had to take off the exhaust manifold. The exhaust manifolds are held on my car are held on by some nuts that thread onto studs. And they're actually deformed. They're not deformed like what you see here. They're deformed in more of a triangular shape, but it's the same idea. If you deform the nut, then it's really difficult to screw it on, and it's very difficult then for it to back out. So it's a simple way of preventing the nut from backing off, just a lot more friction. Of course, you've probably dealt with lock nuts that include some plastic, typically nylon, and as you drive the fastener through these threads, there's a lot of friction between the plastic part in the nut and the threads in the fastener, and so it prevents rotation or backing out. You probably, though, have not seen nut plates. A nut plate is like a lock nut, but they're commonly used on aircraft rather than just everyday things. And you can see the figure H, how the lock nut has a plate that can be riveted to other components in particular that are being clamped into place. So that absolutely prevents the nut from turning. Also, then the function of the I guess they still use nylon in these. I don't know. I've never dealt with them, but it's the same idea as a lock nut. But then the lock or the nylon helps prevent the fastener itself from backing out. The next thing is a nut retainer, and the idea here is that once you tighten the nut down, you can just push the nut retainer on, and the arms that you see there that stick up engage with the threads, and for the nut to come off, the arms literally wedge deeper into the threads, and it's practically impossible to get these things off. Even when you go to fix something and you got to take one of these off, they are a big pain. You typically destroy these things in getting them off. But it does prevent the nut from backing off, and it allows any angle of the nut that you want. Now, the thread form is important, and the first importance is understanding the difference between a right-handed thread and a left-handed thread. If you take your right hand and you wrap your fingers around as if they were the spiral thread, as you wrap your fingers around, if you move your fingers so that they follow the thread, then if it's right-handed thread, your thumb will point in the direction that your fingers have to move to follow the thread. If it's left-handed, then your left hand follows, or your thumb is in the direction that your fingers have to move to follow the thread. So that's the easy way to tell the difference. Of course, you've probably heard righty-tighty, lefty-loosey, and that's a little bit confusing, but that has to do with right-handed threads. If you turn the nut from the top, looking at the top of the nut, if you move that top to the right, well, then you're tightening. Of course, if it's behind something, then you have to think backwards. But there are a few places where you see left-handed threads in everyday life. Typically power saws, chop saws, things like that often have left-handed threads, so that as the blade rotates, it typically rotates backwards. The friction tends to tighten the nut rather than loosen it. You really don't want saw blades just flying off of saws at high speed. That sounds like a recipe for disaster. So speaking of the thread form, I want you to think of the threads as basically a triangular piece of paper that's wrapped around a pencil. Because if you were to unwrap one full thread, the pencil would rotate one full revolution. In the same way, if you were to unwrap one whole thread on a fastener, that would represent one full rotation on that fastener. And that distance along the, that the thread would move in unwrapping one, that distance is called the pitch. It's the distance between two threads, the same point on the two threads. Usually we think about the crest of the thread and the distance between them. Now, there's some terminology that goes with the thread. The sides are called the flank, and the pitch line is just at the center between the highest and lowest point of the thread. That's the pitch line. The area above that pitch line is called the addendum, and the area below is called the dedendum, and this is terminology that's common for gear teeth as well. Now the thread form itself is controlled by two standards organizations, the ISO International Standards and Unified National. Now in Unified National you have fine thread and coarse thread, and there are other standards as well, but those are the two common ones. ISO has a fine and a coarse thread as well, but there's not as much of a obvious distinction between the two. In UNF and UNC, the way that you call out these thread forms is by the major diameter of a male fastener. So the outside of a bolt thread, for example, that nominal diameter, so like a 1/4 inch, for example, and then a dash, and then the number of threads per inch. So like a 1/4 fastener is a 1/4 inch diameter nominal. In reality, it's undersized a little bit and has 20 threads per inch of length along the threaded section of the fastener. Now there's still a pitch, there's still a distance between adjacent threads, but in the case of a 1/4 that would be 1/20th of an inch, right? So the pitch would be a 1/20th of an inch. Now a 1/4 is actually classified as a coarse threaded fastener, and it's a 1/4 1/4 that's the fine threaded in the same size. Now it turns out that actually the female threads, the nut threads, are typically closer to the actual nominal size, whereas the male portion, the fastener that threads in, is undersized. And depending on the class of fit, it can be undersized by a couple thousandths or so, maybe even more, depending on how high quality the threads are that are made and how much load they're supposed to hold. The shape of the thread, though, the relationship between the side angles and basically this triangle I've highlighted in red, is actually the same for both UN and ISO. So the thread form is the same, but the size of the threads are different. Now there are a couple of threads between ISO and Unified National that can actually thread together. The tooth size is close enough to the same, and the pitch is close enough to the same you can thread them together, but obviously that's not recommended. Now what you're probably interested in, though, you may have known all that, what you're probably interested in is the strength of the bolts, or the strength of the fasteners. Now the strength of the fasteners, what we talk about a lot, is something called proof strength. And proof strength has to do with the fastener loaded in a very particular way. So fasteners can be loaded in two different ways, but right now we're talking about tensile loading. So if you think of the fastener as just, let me use this pencil as an example. If you think of the fastener and the load that it's carrying, it's basically being pulled apart. Okay, so it's a tensile load in it, and that's the way that we're talking about when we mention the proof strength of a bolt. The proof strength is just it's a stress rating. It's not actually the force that it can take, so it's more of a material property. It's kind of like the elastic limit of the material, and it's usually about 90 to 95% of the yield strength of the material. So it's more a material property than anything. But understand, we're only talking about proof strength in the context of fasteners that are loaded in tension. And of course the purpose of loading a fastener like this is so that it applies clamping force between two things that need to be held together. Now the proof strength is actually usually communicated by grades. So a grade 2, a grade 5, a grade 8, all these are different bolt ratings that tell you something about the strength. In particular, a grade 2 can take 55,000 pounds per square inch, whereas a grade 8 can take more, about 120,000 pounds, more than double what a grade 2 can take. And you can see the typical uses of these things. Now when I design, I try to avoid designing where a grade 8 is required. Now of course the advantage of a stronger fastener is that you can get away with a smaller, lighter fastener. But if somebody puts the wrong fastener in and you don't have some control over it, your machine can fail. And if the machine fails, if it's an airplane, that's obviously very bad. If it's the tree house I built my daughter, that's very bad, right? I want to know that the fasteners that are used will hold up. So I typically design for lower grade bolts, and that's just an option. I know I'm going to end up with larger fasteners, but in most applications that's okay, and the cost difference is not that much really, okay? Alright, now if you think about the stress in the bolt as you're pulling on this bolt, think about where it's going to fail. Well, usually bolts have a shoulder. I know sometimes it's frustrating because you go and you buy a bolt and you need just a little bit more thread to get it to clamp, and there's this darn shoulder that's unthreaded. And you might think, well, that seems cheap. Why wouldn't they just thread the whole thing? Well, there's actually a good reason. We'll talk about that in a little bit, because that bolt could be loaded in a different way than a tensile load. But for right now, let's just think of a tensile load in the bolt. By the way, the solution to that problem is just to add washers or some spacer. But where is a bolt that's loaded in tension going to fail? Well, it's going to fail wherever it's weakest. Well, where is it weakest? It's weakest where that bolt has the lowest amount of area in its cross-section, and that's in the threaded area. So anytime a bolt is tested, you expect breakage when it's in tension. You expect breakage in the threaded area. Now, that threaded area is not a full circle. In fact, you can see the normal stress area over here in the threaded section in the graphic in the upper left corner of this slide. Now, calculating that area obviously is not just going to be pi d squared over 4. There is an equation for it, but I would recommend instead that you look at page 633, table 19.4, and this is one page you should certainly bookmark in your text. As we go through the slides, I'll try to tell you pages to bookmark, same thing in the example problems. But there's an equation there, but why mess with it? You can just look up the standard cross-sectional area for standard bolts and nuts. Well, standard bolts. D is the major diameter, P is the pitch of thread, but again, you really shouldn't have to use this equation. Now, how much clamping load should we apply? Well, actually, you usually want to use as much of the fastener as possible. It's efficient to have a fastener loaded as much as possible to generate as much clamping load as possible. So we typically try to load bolts to about 70 bolts and screws really to about 75% of their proof load. Now, proof load's a little bit different than proof strength. Proof strength, remember, is more of a strength of materials type of thing. It's a material property. It's a stress. If you multiply that by the tensile area, and understand A sub T is the area in the threaded section, okay, then you've got what would be the proof load. So you multiply the proof strength, whatever material you're going to use for the fastener, times the area, the cross-sectional area in the threaded section, and now that's how much load and force that the bolt could be would be able to take. But we usually only want to use 75% of that available strength or that available load. Now, a lot of times you cannot measure clamp load directly. There are ways to do it, but they can be expensive. So it's very common to use torque instead as an indication of clamp load. Now, this is actually a special fastener system. If you look it up, it's by Unilock. It's an interesting system. I included the graphic here, so I'll mention what it is. It's actually a special nut and a special piece. They're a taper lock type of system, so that as you screw the nut into place, what happens is the threads actually are more like fingers out on the end, and they get clamped onto the threads tighter and tighter, so that you, in tensioning the bolt, you're also tightening down these threads so that it just simply can't back out. Now, the problem with this is that you may not develop the full clamping load that you want as you tension this down, but of course the nut won't back out. Anyway, a lot of times we need to control the clamping load. So how do you do that? Well, this is just an equation that will get you in the ballpark. So if you like equations that give you the exact right answer down to the nth decimal place, that's not this. Okay, this equation is just a rough rule of thumb, and it allows you to calculate a rough torque required to get a desired clamping load. Now, the clamping load is P. The D is the diameter, the nominal diameter, the outside diameter of the threads, and then K is a coefficient depending on whether the threads are lubricated or not. And so it's 0.15 if lubricated or 0.2 if dry. Now, this is usually good enough for many applications. A lot of times we don't need anything better than this. But there are actually more precise models, and your author gives one. And if you think about when you're torquing a bolt or a screw, what is it that you have to overcome? What is it resisting that motion? Well, obviously one is the inclined plane nature of the threads, right? As you turn these threads, you're really advancing the threads into material or into a nut, and so you're basically stretching the fastener. Well, that contribution is taken care of by this first equation for T1. There's some torque required to advance the threads into the material or the nut. But the threads are going to have some friction as they turn also, and so that's the next equation here, T2. But not only that, but if you're turning the nut or you're turning the head of the bolt, there's going to be friction between the underside of that head or the underside of the nut and whatever you're clamping. So there's a third contribution to the torque, and summing these all up together gives you the total torque required to generate a clamping load. Now the only place the clamping load actually appears is in the first equation. That's still P. Okay. Now bolted joints. If we think about an externally applied load to material that's supposed to be clamped together, what will happen is that joint fails if the bolts become loose, right? So the bolts have to be kept tight. So how do we do that? Well, there's actually a really good reason for torquing the bolts down to 75% of their clamp or of their proof load, because what will happen is you'll have a more reliable joint. See, what will happen is that as the clamped material sees external load, that external load will be transferred less to the bolts, and that's a good thing, because if you think about a bolt that's being stretched more as load is applied and then released and stretched and released, you may know something or remember something about fatigue from strength of materials. It's a very bad idea to fatigue a bolt, because that bolt is going to fail. So you really want the bolt's load to not vary much at all. And so if you really clamp it down tight, what will happen is the two pieces of material that are clamped together will have a lot of compressive force between them. But as you have external loads trying to pull these pieces apart, all that will happen is the main thing that happens is that the compressive load between the two decreases, and the bolt doesn't see as much variation. So it's important that you clamp things together tightly and don't have loose gaskets between them, because if you have a soft gasket between them, the bolts, it turns out, will see most of the external load. Now, if there's hardly any external load, this is not really a concern. But you can calculate the amount of force in the bolt, that's F sub B, and the amount of force that's clamping the joint together, that's F sub C, due to an external load, F sub E. Now, P is the initial clamp load, F sub E is the externally applied load, and the K's that you see, K sub B and K sub C, are the effective spring constants of the bolt or the fastener and the material that's being clamped together. So it's a good idea. There's multiple reasons for having the bolts nice and tight in assemblies. Now, there are methods of bolt tightening. There's the turn of the nut method. If you think about what's going on when you thread a fastener into something, well, if you make one whole revolution of the fastener, the threads of the fastener have to advance into the nut or the material that's being clamped by one whole pitch, right? So if you know the bolt diameter and you know the elastic modulus of the bolt, and you know how far the threads move, well, you can calculate how much more stress that is, and therefore how much more load that is. That's just a strength of materials problem. So the turn of the nut method, you may have seen this if you ever rebuilt an engine. If you put a cylinder head onto the top of a block and you put the cylinder head bolts in, a lot of times they'll say tighten to a certain torque and then add a quarter turn. Well, the reason for that quarter turn is because you're advancing the fastener by 1/4 of a pitch, and that's guaranteed to add a particular amount of stress or force onto the cylinder head. So that's the turn of the nut method. There are also other tension control methods. This is a Hux system, I think is the trade name of it. It's a special fastener, and you can see it there on the left before installation. The tool during installation is represented by the black lines, and it's really two concentric. Think of this as a socket on the nut and another spline drive in the middle. And what happens is the socket is used to hold the nut still. The spline drive actually turns the fastener, the entire body of the fastener, in order to drive the fastener into the nut farther. And what happens is the splined section of that fastener is connected to the fastener by a very precisely controlled section of material, and that material is designed to break at a very particular amount of torque. And so after installation, that little segment of spline breaks off, and you know that the fastener is at the proper torque because the splines broke off, and they're guaranteed to break off at a particular torque. So that's another method that can be used. Relatively expensive, because those are relatively expensive fasteners. There's also wavy flanged bolts. I couldn't find a good picture of this, but they're kind of similar to direct tension indicating washers. And now there is a standard that controls these, and the basic idea here, these are a lot like just regular washers, except they have some material that's, you can see it there in the picture, it's just up, and what happens is as you tighten down the fastener, those raised sections are clamped down, and once they're clamped all the way down, well, there's a certain amount of force required to clamp them down, and you know then that you've got the right amount of tension and clamp load in the joint. Now, a slight variation on these that are still also controlled by the same standard is the type you see, and I can't remember the right name for these. There's a name that has to do with the fact that there's some silicone, colored silicone, that squishes out once those little bumps flatten out. And then you can see that they've squished out, and so you know you're at the right tension in the joint. There's a more expensive method. It's the ultrasonic tension measurement system, and there's many manufacturers of these out there. These are just a handheld device that costs usually $3,000–4,000, and what it does is it passes an ultrasonic wave through the fastener. So you just put the probe there on the end, and it generates sound. It's ultrasonic sound you can't hear, and it measures the echo, the amount of time it takes for that sound to go all the way through the fastener and return. And based on how long that takes, it can tell you how tight the fastener is. Now, this may seem strange at first, but it's really not. If you've ever played guitar or you know how a guitar works, you know that when you put a string on a guitar, you use a nut basically to tighten it down on the head typically of the guitar. And as you put more and more tension and you basically stretch that string, the frequency, the vibration frequency of that string changes in the same way. And the reason it changes, by the way, is because the speed of sound changes in the string when you tighten it. That's what's going on here. As you tighten a bolt, it's a lot like tightening a guitar string, and the frequency, the speed of sound through that bolt actually changes, and you can measure it with these devices. Now, obviously, if you drop and break this thing, you're out several $1,000s, and so that's one reason they're not used. Also, it takes special training, and most of the time, that level of precision is not really required, but it is something that is available, though it's not common. The tighten to yield method is another idea. It's fairly simple. If you think from strength of materials, you know that as you take steel and you stretch it, it will eventually get to a point where it's no longer behaving quite like a spring. Right? With a spring, as you stretch it, it takes more and more force to stretch it farther and farther. Well, there's a point in stretching material that material will so-called yield, right? Especially if it's not a high-strength steel or something. What will happen is you'll get to a point where stretching it further doesn't require any more force, okay? And that's called the yield point. In the same way, if you're torquing a bolt and that bolt or screw, the threads are advancing in material, okay, so it would be a screw in this case, you'll get to a point where the shoulder of that bolt is stretching and it's yielding. And it turns out what will happen is basically the amount of torque required to go farther does not continue to increase because the fastener is just yielding. Now, of course, this is problematic because once you've yielded it, you've got to stop. You don't want to go all the way to failure. And also, you can't really reuse that fastener because once you've yielded it, it's stretched too much, you're in the stretch zone, and you don't want to keep yielding it further because you're getting closer and closer to breakage. A lot of bolts in my car, when I rebuilt the engine, are tighten to yield or torque to yield bolts. And I had to replace them when I rebuilt the engine. Now, it turns out there's actually an injection pump on this car because it's injecting diesel at relatively high pressures, and there's a sprocket on the end of the injector pump that has to be mechanically timed. So it's kind of a weird system. You hook up a computer or something to the car's ODP, OPD, onboard diagnostic, OBD port, OBD2 port. So you hook up a diagnostic port and you tighten down these tighten to yield bolts on this sprocket. You turn the car on and you look at the timing, and from the graph you see, you know whether you need to advance the timing or retard it a little bit by changing the angle of that sprocket. So after you've tightened these torque to yield bolts down, of course you're supposed to not yield them, but obviously you might to get the sprocket tight enough. Well, then you're supposed to loosen them, change the angle of the sprocket, and retighten them. Well, that defeats the purpose, so I threw those out and replaced them with bolts that didn't yield at such a low point, and it works fine. So I'm not a big fan of tighten to yield, but it is one option. There's another type of bolt that's become more common recently. There's a company that started this within the last, I think, 10 years or so. I don't know how long they've been around. I heard about them recently. They're called smart bolts, and they're not really anything all that special, but it's a pretty clever idea. They actually buy off-the-shelf bolts, they drill holes in them, and add their indicating system to it. I'm sure it's patented and all that, but it's really interesting because all you do is you look through a window as you tighten it, and once you get to the right torque, the color changes. And so you can see here that the bright red is loose, and it gets to more of a black or dark red color when it's tight enough. And it's actually a very simple system. The bottom portion of a reflective material is attached to the end of the bolt inside. And what happens is as you tighten the bolt stretches, and that pulls this away from the window, and the window darkens. It's a really clever, simple system that's fairly reliable and accurate. And the nice thing about it, too, is you can pull these out and reuse them as you wish. So smart bolts are kind of taking off, and I've heard a lot of companies starting to use these. Okay, so now let's talk about thread stripping. We want threads to not strip, and so if you think about it, how many threads do you need so that the threads cannot strip once you tighten them down? In other words, you don't want the threads to be sheared off of either the nut or the bolt. And I've got a picture here that indicates both of those happening. So the question is, how many threads, how long does the nut need to be to have adequate threads so the threads are at least as strong as the body of the bolt? So, you know, as you tighten it down, eventually you'll get to a point where either the threads are going to fail, but you're really close to, or maybe the body of the bolt fails first. Of course, the body's not going to thread, is not going to fail. The threaded section would fail first, but you see what I'm saying. So how long does the nut need to be? Well, it turns out it depends on how strong the female threads or the nut threads are and the male threads or the bolt or screw threads are. It depends a lot on whether or not they have equal strength or different strength. So in the case where both of those have the same strength, the equation is actually fairly simple. It's over here on the right. The engagement length, or the length that the nut needs to be, is a function of the tensile stress area of the bolt. So this A sub TB is what we knew before as A sub T, and is on page 633 in table 19.4. That's just A sub T. That's what we called it before. So that's the tensile stress area. That's a cross-sectional area in the bolted section, and of course that's the area that's going to fail anyway, so that's why it appears here in the equation. P sub D, or pardon me, not P sub D, PD sub nominal looks like two different things, but it's not. It's the nominal pitch diameter. Okay, so it's just one variable. So, you know, if you're using a quarter-inch fastener, it's close to a quarter-inch. It's actually at the pitch, which is the halfway point of the thread. So it's actually a little bit smaller, but you can look that up in Machinery's Handbook or wherever. That's a fairly common, easy thing to get. And then pi is a button on your calculator, and 4 is a number as well. But that's how you calculate the effective length needed so that the threads are just as strong as at least the tensile stress area of the bolt. Now, if you want the shear area, there's an equation here for calculating it, but look at the bolt and the nut, and you can kind of begin to understand what they mean by shear area. It's the area that you can see once the threads have been sheared off. Now, it's not really at the root; it's at the pitch line, and that's why there's a LE over 2 here. You're taking a different section of the threads. But if you need it, there it is. Of course, that's not as useful an equation. The engagement length is the most useful equation here. Now, if the internal threads are stronger, well, what does that mean? What are the internal threads? Well, that's the nut or the female threads. If those are stronger and the bolt or fastener is weaker, then what you're concerned about is the thread stripping on the bolt or the fastener. So in that case, you'll notice that a lot more things reference the bolt itself. So we've got the bolt tensile area and the bolt shear area as two variables that are involved with these equations. Okay, and of course also we're dealing with the bolt's minimum pitch diameter. So what is that? Well, that's moving considering the threads on the bolt closer and closer to the root diameter, and of course that's where the failure would occur because the bolt's the weaker material anyway. So you might notice that this engagement length equation is a little more complicated than the last one, and I forgot to mention what lowercase n is. It's the number of threads per inch, so it's not pitch, it's number of threads per inch. And of course, if you're going to use this for metric threads, you'd have to figure out what that would mean. But anyway, and actually there should be some conversion factors in there too. So these equations would be good for English units only. Now what about external threads stronger? In other words, if the bolt or fastener has the stronger threads, think about a titanium bolt going into a lead, a piece of lead, or even the examples we've got here. If the internal threads are aluminum or cast iron or something like that, then we have to consider the strength of the bolt and the strength of the nut, the strength of the material itself, and you see that those terms appear here. Now you might look at this and say, well, why on earth wasn't this something that was in the last equation? Well, we're getting to the point where these equations are they're based on first principles, but we're not as much worried about where they come from. We just know that they work, so we use them. Okay. You'll notice here too that we've got a few different things. We've got the nut's maximum pitch diameter, and we've got the bolt minimum outside diameter here in these equations. So we just trust that the equations work and use them. A lot of the equations in these books will be understandable, and they'll be either rules of thumb like the torque equation I showed you a minute ago, or there'll be equations like this where we just basically have to trust that they work. What about frames? If we want to design frames that are effective, we need to design them to resist bending, and typically that's when we use frames. Of course, we also design frames to resist torsion. Here's a simple frame that I built. I bought a saw from Level 1 for 20 bucks. They were getting rid of it and they didn't want to just scrap it. It's a nice industrial saw. I still haven't got it going yet because it's got a 3-phase 220 motor, and I can run it off a single phase at my house, but it requires a little bit of finagling to make that work. And I haven't got it running yet, but I decided I was going to build a frame for it because other things on my to-do list. When I build a workshop, I'm going to put this in the workshop. So at least I got the frame built for this thing, I guess. Well, I built the frame out of members from old garage doors, or not garage doors, but garage door openers that I have. And the members are just basically a T shape like this, and so you got the bottom part and then a T that comes off of it. And I had to think about how I was going to orient them so that I could do the welding and have a strong frame. But I carefully designed it so that on the ends and actually the back also I can put what's called a panel stiffener. So if you look at this, the picture on the right, you see some plywood sort of behind the blower that I've got there. And that plywood is actually screwed into the frame members, and that prevents wobbling like this of the frame. And I included sort of a detail of one of the corners so you could see how I welded it. Well, that's not a very long weld, and so the amount of resistance there to bending the frame members or pivoting them relative to one another is relatively low, and I wanted to include some stiffness there, so that's why I put that panel stiffener in and made it so that I actually have panel stiffeners for the back and the side, but I had to take them off for the picture so you could see how this works. Now, it turned out I wasn't using the saw, and I needed a fan that I could move around. You may or may not know this, but mosquitoes actually are not very strong flyers. And so if you have a fan blowing on you while you're working, even in the heat, it'll help keep mosquitoes off of you. So that's what I use this thing for, is to make myself more comfortable and to keep insects away from me when I'm working outside. So I've got a little switch box there on the bottom. It's a 2-speed fan, so I've included switches so that I can have a high and a low speed, and of course an on and an off. But anyway, to keep frames from bending, you want to keep lengths of beams short. Even if you're making a truss, you want to keep the length of the members short if possible, but you want to increase the chord distance in a truss. You want to place loads close to supports. So you notice here that, of course, there's a frame involved in the saw itself, but I've put supports close to legs. So I didn't really run a lot of load down through the horizontal members. I ran it down through vertical members directly to the wheels. You want to maximize moments of inertia in the direction of bending. So this is something you should understand intuitively from strength of materials, but that just means that you want material to be relatively tall if there's going to be some bending action of the members. Use stiff materials. Most of the time we use steel for things like this because steel has a relatively high Young's modulus. And make connections as stiff as possible. So you see I didn't just tack weld this, I put a line of weld so that they can't, I was trying to resist rotation. Now, some more information. You want to brace corners, so you could use, a triangular shape. Using diagonal stiffeners is another way. Using panels. You saw a panel stiffener on the last photo. And rather than going through all this, you can read these. What about if we look at a well-designed frame and a poorly designed frame? The frame on the upper right is a Yamaha frame. I don't know what model. I just grabbed the photo online. And the little scooter you see there in the bottom center of the presentation slide is from some plans you can buy on eBay. Well, just looking at these, I hope your intuition is strong enough that you can see that the scooter frame is a horrible design, and the Yamaha frame obviously shows some experience and some knowledge about frame design. Let's just start off contrasting, for example, the fork support. So you see the fork support on the left in the scooter and on the right in the Yamaha frame. Look at the difference here. Yes, both connect the upper and lower portion of that support to the frame. But look at what Yamaha did. Instead of taking the supports and pulling them together, they pulled them apart, right? They turned that into an upper and lower cord of a truss, which is a really good idea. In fact, one of the recommendations here, use trusses. You'll get great stiffness and lightweight. That's exactly what Yamaha did. What did the scooter designers do? Well, somebody drew this thing probably on their computer and started selling them. Well, they ran those two together. They didn't bother with trying to build a truss out of this thing. Instead, they're relying on the strength of just the beam, this lower beam section. And of course, the reason they did that was so it's comfortable and you don't have to swing your legs over anything. But you can see the disadvantage here too. Where do you think that frame's going to break? Think about it for a minute. It's pretty obvious. If you said where the fork supports come back to the long members, that floor sort of, you're absolutely right. That's where the stress is probably going to be the highest, and there's going to be a lot of bending there, and it's going to break fairly easily. So you want to put stress concentrators, which is what that really would be, at areas of low stress, but that's an area of high stress. What about gussets or bracing? Well, look at what Yamaha has done on the back. Probably the back of this frame on the left-hand side is an area where suspension components and things would have to be mounted. But look at the gussets they've added there. They didn't just run two beams together for support. They added in some panels and some welded pieces to make that much stiffer. They've used bracing. If you look, there's a lot of bracing going across. So they've got basically two trusses side by side that are connected together. I see very little bracing in the other design, in the scooter design. So hopefully, a lot of this is sort of intuitive. Another thing that they've done in the Yamaha design, do you notice the triangle there near the back of the frame? You notice a large open area, right? That's an open area that could be a weakness, right? Because it's sort of like a four-piece member that can I don't know what the word is, but deflect back and forth. Now, the design decision they had to make there was where we're going to put the engine, right? You can't just make a small triangle. That makes it difficult to fit the engine. But they did reinforce the frame in the back with a triangular piece. Now, I'm not talking about the part that goes way to the back, but the way they've got a member going down, it looks kind of cluttered there in the center, and it separates the engine compartment from the rear. Well, what about resisting torsion? Well, here's a simple frame where the first has just conventional cross braking, and given a unit torque, this frame, of course, we haven't shown the particular dimensions here, but it deflects by 10 degrees or so. If you use that bracing in the center instead of traditional cross bracing, if you use it instead to make triangles and make diagonal bracing, you will reduce the deflection significantly. Notice we went from 10 degrees down to less than a degree. That's very impressive. And if you use double diagonal bracing, you can reduce it even more. If you ever get the chance, look at a toddler's toy, something they ride on. Look at the bottom of the seat. You will probably see this because plastic is not a particularly stiff material. And if a toddler is going to sit on it, you don't want it bending, right? It's going to be relatively thin material, so what do? Well, you add double diagonal bracing and you make it torsionally stiff. Another thing to do is include members that are stiff themselves. So if you imagine a thin extruded piece of material, so it extrudes out toward us, and you try to bend it with this relative size, we get about 24 degrees a little less than 24 degrees of rotation if we put a torque on it. If you take that same amount of material and make a C channel out of it instead, again it's still extruded, and we apply a torque to the end and hold the opposite end fixed, with a C channel you get actually a little bit more deflection because there's less material farther away from the center. It gets even worse if we roll this material into a hollow tube. But if we close that tube, as soon as we close the section, the amount of torsional rigidity just skyrockets, and the amount of deflection from that same value of torque, whatever it would be, goes down quite a lot to less than a degree. Even if it's a non-optimal shape like square tubing, there's very little deflection. You get a very highly torsionally stiff cross section. And if you use those members to build a frame, then that frame can also have relatively high resistance to torsion. You typically want to avoid open sections with thin materials if you're building a frame in order to resist torsion. You do use diagonal bracing in order to resist torsion, and make all of your joints and connections rigid. So now let's shift gears a little bit and let's talk about loads on bolted connections. As a matter of fact, we've already seen how we can apply loads to a bolted connection in tension, but instead of doing that, now let's consider what if we have shear loads. So look at the image off to the left. We've got a bracket that's supporting a load as just a motor or something, and we're trying to attach the bracket to the rigid frame so that the motor load can be supported. Now hopefully you realize that A provides a moment arm for the load P, the weight of the motor, and whatever else the load applies to the bracket, so that it's going to try to tend to rotate about the centroid of that bolt pattern. Now if you think about it, and I ask you the question, how many bolts do we need at minimum in order to support this bracket? If you think about that for a second, you might say, well, it's one, because if I clamp that bolt down tight enough, I'll get friction between the surface of the bracket and the surface of the rigid frame, and it won't rotate. Technically, you're right, but in the method we use for sizing bolts, given a pattern of bolts, in order to resist whatever load we apply, we assume that there's no friction between the two materials, and that way all of the load is being carried in shear by the fastener. Okay. Now, one important thing about designing with fasteners and bolts in shear, this is where you do not want the threaded section to be in the interface between the two members being clamped together. You think about it, it makes sense, right? Because if you have a threaded section on that line between those two blue pieces of material that's being clamped together, you actually have less cross-sectional area than in the shoulder of the bolt. Because the shoulder of the bolt is just a circle, right? It's a larger diameter and there's less material being taken out. Not only that, but the threads actually provide stress concentration, so it's as if you have even less effective area. So it's very important in applications where fasteners are going to be sheared, or shear load applied to them, that you do not put the threaded section in the joint. Now, I'm not going to show you the details of the method that we use to size the fasteners here. I'm just going to tell you a little bit about it. You'll see the details of it in the example problems I've got. But what you do is you design a pattern, some convenient pattern, something that makes some sense. You know, at least 2 bolts. You decide, okay, it would be convenient to put bolts around a certain pattern like this, maybe 4, maybe 3, 8, whatever. And then the method allows you to calculate what diameter of bolt would be required in order to support a given load. And if you find that the diameter is ridiculously large, well, you need to move the pattern out farther, or you need to use higher strength bolt, or you need to add more fasteners to your design. So one thing to add about this is it turns out that the load that each bolt has to support will be a little bit different, because it turns out you'll have a shear load and a moment load, and those loads can either add to each other or subtract from each other and make one of the fasteners a critical fastener. So one of the things you have to do in the method is figure out which fastener is critical and size for that fastener, assuming the rest will be the same size. Now, bolted connections are not the only option for connecting that bracket to the frame. You could also weld it together. So how do you decide how big the weld needs to be? Well, there's a couple different types of welds. There are so-called butt welds, where you take 2 pieces of material, you just butt them together. Typically you include a groove for the weld filled material to go into and to make sure that the weld material goes through the entire thickness of the material. But typically when you butt weld something together, the weld material itself, as long as you fill up the entire groove, the weld material is stronger than the surrounding metal, and so the weld is not going to break because you've actually increased the strength of the part. Now there's a lot of practical considerations because of course the welding typically cools very quickly, and so you get a fairly brittle material, and you can end up with fatigue failure easily in the brittle area. But basically we don't bother to size butt welds because you're going to end up with a weld that's stronger anyway, and you might need to stress relieve it or treat it, but that's more of a materials processing thing, so we don't discuss it in this class. Rather, what we're interested in is if you have, imagine two plates and you're going to weld them together, well, you're probably going to put a fillet weld at the interface between those two. So imagine the fillet weld is just, its cross-section is a triangle, right? So if you zoom in on it, you would and look at a cross-section of it, you would just see a triangle. And the question becomes, how long a leg does each side of that triangle need to be? And we usually assume a 45-degree angle, and the question is just, how long a leg are you going to have? Well, what we do is we treat the weld pattern as a line, and we calculate the load from well, I should say the stress, essentially, due to the various loads applied to that weld. Now, it's not really the stress. It kind of looks like it. If you look at all four of these equations, you'll notice it's basically a load over what looks like an area. So we've got a load P over an area A sub W, a load V, which is a shear load, over an area A sub W, but that's not really what we're doing, because A sub W, S sub W, and J sub W are actually what we call geometry factors. A sub W actually has units of length, or dimension of length, and so lowercase f in that first equation has units of force per length. So it's not exactly a stress, but it's kind of like a stress, and that's kind of the way we treat it. And you'll see more detail about this in the example problems. Interesting side note here, all of these loads have direction, and so P, V, M, and T, which is a torque type load, M is a moment type load, all of these loads have direction, and so the resulting, let's call it a stress in the weld, all these F's also have direction. And when you add them together, you have to add them vectorially. So you'll see the details of how to do that in the example problem. But once you've figured out the amount of load in the various sections of the weld, you can figure out how large the leg needs to be given a weld strength. In other words, if I use a certain rod, how much allowable force per inch of weld length is required. So that gives you your leg size. Now, in doing this, a lot of times it turns out loads are relatively small and welds are relatively strong. That's why they're used so much, because they're very strong things. Interesting side note here, a lot of times you'll calculate a weld size that is just ridiculously small, like a 32nd of an inch. Now, if you have ever tried welding, you know that hand welding a 32nd of an inch bead is a joke. Nobody that I know of, even the best welders, could really do that unless you get down to somebody that's really good at TIGging and using a very small setup. It's just not practical. So a lot of times what you'll do is you'll do the calculation to show due diligence and that you've made sure that the weld is strong enough, and then you specify a much larger reasonable size weld. So it's very common. It would actually be more expensive to try and make a very small weld that matches your calculations. So that's one practical consideration here. Another practical consideration is that the method that I'm going to show you actually is not capable of calculating a weld leg size for just any old pattern, any just random pattern of weld. In fact, there's only 9 patterns that we can calculate. And there's a table in your book. I don't remember the page number right off, but you should find it. It's in chapter 20. And mark it. Definitely put a tab there. It's well worth it, because you're going to refer to it every time you try to solve a weld problem. But these 9 weld patterns are very common, very useful patterns, and they are the patterns that we will be able to solve. So this is the table, kind of the solid gold table for weld factors, and it helps you figure out which case you need and what your geometry factors are, because you notice for each of these 9 cases there are S sub W, J sub W, and A sub W equations, so that you can calculate the magnitude of all those factors for each of these scenarios. Now, it takes a little bit of understanding to know how to work with these, but again, I'll describe that in more detail in the example problems.